Hi, my name is Carlos Villegas. I'm the Electrification Industry Manager at Speedgoat. In this webinar, we will present how to advance electrification using real-time testing, from renewable energy integration to the development of battery electric vehicles. This webinar provides a general overview of how you could use real-time testing for your developments in electrical systems and power electronics. While I will not go in detail for each topic, you will receive a list of links for resources like videos, web pages, and real-time ready Simulink files to go deeper in the topic of your interest. We have the following agenda. After presenting the benefits of real-time testing, we'll introduce the unified real-time testing platform composed of Simulink and Speedgoat hardware. We'll then present the electrification megatrend and three growth segments: power electronics, power systems, and power and energy management. We'll go deeper in each of the growth segments via demos showing the advantages of using real-time testing. We'll then cover high voltage DC transmission and renewable energy integration with a focus on grid-tied inverter development. Afterwards, we'll discuss power systems with examples for the electric grid and electric vehicles. Finally, we'll cover the development of battery and fuel cell energy storage. So we'll cover many topics during this webinar, but I'd like to emphasize the following three key takeaways. First, that you can use Simulink and Speedgoat hardware as a unified platform for developing power electronic converters, electric motors, energy management, and power systems controls. Second, that real-time testing is a key step between desktop simulation and embedded code generation for developing electrical systems. And third, that you can use hardware-in-the-loop simulation together with test automation to thoroughly test both embedded controllers and electrical components for normal and fault operating conditions. To show the benefits of real-time testing, let's say our joint task is to develop, test, and implement new electrical components. It could be electrical powertrains for electric cars, a grid-tied inverter, aerospace control systems, or a mobile device. We need to address the requirement to make more efficient and often also more complex systems, and we seek to do it faster and better. In particular, these questions arise. How do you swiftly iterate over product designs? How do you safely test your equipment? You should be focused on the design and testing of controllers for complex system dynamics. You should not be constrained by the infrastructure to do that. So let's look at how you can benefit from model-based system engineering from early design all the way up to field deployment. This timeline represents a model-based design path without iterations, with the objective of showing you how controls development and testing can benefit from real-time testing. With model-based design and real-time testing, you can go from early designs through all the iterations and test cases via flexible and powerful prototypes. It is not only about rapid controller prototyping or hardware-in-the-loop testing. Today's systems are way more diverse. So we'll touch base on use cases such as field-oriented control, auto-tuning, power hardware-in-the-loop, or the emulation of components like resolvers or battery cells. Your workflows may deviate slightly, but we are pretty sure that you'd agree on the following three main motivations for real-time based controller prototyping. Test early to prove that your algorithms work in real-world dynamics. You may find better trade-offs and tweak performance. The unified workflow provides a path from desktop simulation to automated testing with flexible and powerful hardware. This unique combination allows you to worry less when testing. Ultimately, you can be more innovative, expose design flows earlier, and shorten time to market. But we know that you want to accelerate your control testing. Now you can use PID Auto-Tuner and the field-oriented control Auto-Tuner to avoid manual testing. Front-loading verification and validation tasks commonly is the main motivation for hill testing. It may be that the hardware prototype is not available or you gradually integrate components. You want to resolve design flaws and test edge cases in a safe environment. What do you need for hill testing then? Certainly a platform that runs your plant in deterministic manner while being connected to sensor and actuators. and that would allow for plug-and-play interfacing and test automation. Ultimately, this will help you deliver embedded software faster with lower risk. Adding a high-end power amplifier, you can connect an actual power component to your virtual plant. This is called power hardware in the loop. Typical applications include connecting a solar inverter to a virtual grid or connecting an electric powertrain to a virtual electric motor. After going through the benefits of real-time testing, let's briefly present the unified real-time testing platform. The real-time simulation and testing platform from Speedgoat and Matpor simplifies your workflow and lets you design and test better controllers faster. You can then innovate and you're not constrained by embedded testing environments or with the hassle of integrating different solutions. Benefit from a plug-and-play real-time solution that shields you from interoperability issues. Experience the unity of simulation and testing with real-time target hardware, all directly from MATLAB and Simulink. The seamless integrated solution is composed of two main components. The first one is Simulink Real-Time, the solution for real-time test and simulation from within MATLAB and Simulink. It comes with several host capabilities that allow you to easily create, control, and monitor your real-time applications, and serves you as your real-time operating system. The second component is a powerful and scalable Speedgoat real-time target computer equipped with I/O. The real-time application created from Simulink models runs on it together with the Simulink real-time operating system. No matter whether you're prototyping control strategies or testing controllers against your digital twins, seamless connectivity shouldn't be a hurdle for you. We are supporting key protocols from all industries, including DNP3 and IEC 61850. More than 200 I/O modules are available and ensure that your workflows remain uninterrupted. Let's look at connectivity also from another angle, independent of just protocols. I/O also means access to sensors and actuators, for example, measure quadrature encoder signal for rapid controls prototyping or emulate a resolver for hill testing. PWM signal generation and capture, such as for motor controls, is an example that requires high frequencies and ultra-low latency. Also think about several real-time systems with multi-core CPUs and several FPGAs sharing computational load and operating synchronously. A key enabler for your seamless development workflow is the stress-free I/O configuration. I/O and hardware of any kind is represented by Simulink blocks. Placing them in your model and configuring I/O or protocols is done within Simulink. Speedgoat offers two types of FPGAs, configurable ones and Simulink programmable ones. Configurable FPGAs allow you to use high-frequency I/O and lots of protocols without FPGA programming knowledge. There are many code modules represented by Simulink driver blocks. And you can configure your FPGA on the fly and directly from Simulink. Speedgoat provides different configuration files so that you can get the best performance out of the I/O module for dedicated applications. FPGAs can also be used to schedule execution of subsystems, the entire real-time application, and as said before, individual I/O modules, or even to synchronize multiple target computers. Programmable FPGAs allow you to have both parts, your algorithm and the signal I/O in the FPGA using the HDL coder workflow from within Simulink. Speedgoat provides you with ready-to-program I/O and protocol driver blocks, so it doesn't necessarily become more complicated, because you can leverage and start rapidly using hardware-proven example models. Ultimately, you have more flexibility for your advanced use cases. Several FPGA I/O modules allow using both workflows, so it is possible to start simple with the configurable workflow and evolve to the programmable workflow as you go on. Regardless of the workflow, Speedgoat FPGAs work like any other I/O module and can be reconfigured. Allow me to share a concrete example about FPGA-enabled data acquisition, namely a success story by our customer TAE Technologies. TAE Technologies focuses on clean fusion energy, therefore quite relevant for electrification. Their fusion reactor named Norman handles hot plasma of around 30 million degrees Celsius. A challenge is keeping the plasma well centered in the reactor, which requires state-of-the-art feedback control techniques. Controls require magnetic field data from about 400 sensors to be logged and stored at 2.5 MHz. For data acquisition and two compute systems that communicate using fiber optic multi-gigabit transceivers and Aurora, allowing for super fast and deterministic data transfer while meeting best-in-class I/O latency. To develop controls, TAE relies on Speedgoat programmable FPGA I/O modules, HDL coder from MathWorks, and of course Simulink. Having gone through the benefits of real-time testing and the unified real-time testing platform, let's discuss electrification megatrend and how real-time testing supports it. We live in a world dependent on electricity, and that dependency is only growing. At the same time, greenhouse gases are trapping heat and warming the planet. Ambitious goals support CO2 emissions reductions for core economic sectors including transportation, electricity generation, transmission and distribution, industrial production, and buildings. At the same time, digitalization, automation, and autonomous systems dramatically change the way goods and services are sourced, produced, delivered, and consumed, significantly impacting requirements for the overall electrification infrastructure. As a result, in the electrification megatrend, we see a faster than ever adoption of new power electronics, power systems, and power management technologies that are not only improving energy efficiency and storage, but also that they are enabling the competitive use of sustainable energy sources. To assess the impact of real-time systems in the electrification megatrend, we can consider three different growth segments: power electronics and motor control design, power systems analysis and control design, and energy and power management. All areas are driven by market and technology developments. For example, the increasing adoption of renewables and the use of power electronics for electric transportation is driving the power electronics growth. The decreasing cost of power-rich batteries is also driving growth in the energy and power management segment. These three growth segments of the electrification megatrend have an impact on many industries and even our daily life. Power systems analysis and power systems control design cover the electric grid infrastructure, from traditional sources and microgrids to renewables, energy storage, and FACTS, or flexible alternating current transmission systems. Power systems looks at the analysis and control from a system level. And it also covers electrical transportation, including trains, ships, airplanes, and cars, as vehicles can also be seen as a type of microgrid. And when we look at the component level, we can consider the segments of power electronics and motor control design, as well as energy and power management. Here we can also consider the development of inverters, motors, and batteries, for example. At a component level as well, electrification also covers consumer products like computers and also medical products like ventilators for respiratory support. Let us continue with real-time testing applications for the power electronics area. Starting with power electronics, we will go through the three market segments to talk about the benefits of real-time testing. In general, power electronics converters and their associated digital controllers are an interface between a power source and a load, like controlling an electric motor or generator, charging a battery, or converting three-phase voltage into high-voltage DC for transmission over long distances. Electric motors and generators are a typical application of power electronics. For example, wind turbine generators require power converters to provide grid-compliant electricity for the power grid, Our electric vehicles require power converters to adjust the DC power from battery packs into three-phase power for the electric motors providing traction. Real-time testing addresses a few challenges for electric motor control development. A key challenge is writing C and HCL code for microprocessors and FPGAs by hand. This is error-prone, especially when you work in a team and you need to maintain it and upgrade it. As a result, software errors are oftentimes found at a late project stage only. The unified platform of Simulink Real-Time and Speedgoat provide automatic code generation from Simulink with readily available sensor interfaces and communication protocols. The protocol stack and signal processor is configured from within Simulink, and the same model can be used for code certification. Developing and verifying complex control algorithms can be challenging, as for R&D, you typically require much data logging and tuning. This can delay your development, as instead of focusing on the key innovations of your product, you need to manually set up sensor interfaces or even deal with communication protocol stacks. Rapid Controller Prototyping provides a powerful control testing platform with on-the-fly data logging and tuning for controllers. Rapid Control Prototyping is ideal for rapidly verifying and validating designs. Tune and see real-time results from Simulink or within a custom graphical user interface. You can also reduce manual tuning. Validation and verification of your final controller also presents challenges, like having to wait for hardware availability. That may be for the embedded control platform or the power converter. Finally, it is possible to emulate your plant using hardware-in-the-loop testing. You can not only start testing before your power converter is available, but you can also test your virtual plant in extreme conditions without risking the real motor inverters, or even use PowerHill to test actual motor inverters with virtual motors using power interfaces from a few watts to megawatts. Real-time testing supports new developments for electrification as an integral part of model-based design. Let's see how real-time testing integrates into the development process for a power electronics or electric motor control design application. For control development, the journey typically starts by defining requirements and simulating both plant and controller in a desktop environment. Then once an initial control design is ready, our customers move into controller prototyping on a real-time target computer. Before connecting to your hardware prototype and potentially damaging it, you would employ hill testing using another real-time target machine, mimicking the input and output interfaces of your prototype, running the same plant models that you are designing from desktop simulation. From your workflow, there is no impact because Simulink is your central development platform, so you have no constraints for your design iterations. And before connecting your precious hardware to the embedded controller, there are two testing tasks that you would want to conduct. The first one being hill testing with the code running on the embedded target. The second one is another controller prototyping step involving a real-time target connected to the hardware prototype, for example, to fine-tune the controller. At the end of this agile and safety-oriented workflow, hardware and embedded controller can be put into service. Let's have a look at the demo on the electric motor control kit, including Speedgoat and MathWorks products. We use a baseline real-time target machine with a Simulink programmable FPGA, a three-phase inverter from Speedgoat, and a brushless DC motor. With this demo, using Simulink, Simscape Electrical, and the motor control block set, you can quickly get started with field-oriented control, parameter estimation, rapid control prototyping, and even hill testing. In this demo, you can tune the current inner loops and the velocity outer loop of a brushless DC motor. This is done using a field-oriented control auto-tuner from motor control block set. This model uses field-oriented control, so in the current loop, we will see the Clark and Park transforms, as usual. But also, now we'll have the field-oriented auto-tuner block that will be able to insert perturbations, and it will also be able to access sensor data in order to calculate the gains for the PI control loops. When we start the desktop simulation, we will see that the speed tracking is slow at the beginning, underdamped. It will After a few steps, it will insert perturbations, and the field-oriented control auto-tuner will automatically calculate the control loop gains. And by doing this, it will achieve certain bandwidth and phase requirements as we said before. Now we can move to our real-time testing platform. We will again use the field-oriented control with the field-oriented control auto-tuner. As we see, the motor starts spinning, but initially the speed tracking is not great. Perturbations will be inserted in both control loops, and then the PID parameters will be obtained. As you can see, after the perturbations are inserted and the PID parameters are calculated, the tracking performance is much better. In addition to the challenges already mentioned for controlling electric motors and generators, power converters have other challenges like the use of high switching frequencies, the control of multi-level converters, and having safe testing conditions. Real-time testing with Speedgoat hardware enables you to control and simulate wide bandgap semiconductors with closed-loop bandwidth of 2 MHz, high-speed analog I/Os, and switching dynamics supporting up to 200 kHz switching. Furthermore, modular multi-level converters can be controlled using fiber optic links and emulated for hardware-in-the-loop testing with tens of modules per target computer, all while staying in the unified test platform of Simulink and Simscape Electrical. Let's have a look at a customer example, in this case Supergrid Institute in France, who leveraged a Speedgoat system to develop a new high-voltage, high-power DC-DC converter with rapid control prototyping. This DC-DC converter shall support efficient DC transmission in supergrids, requires switching frequencies of 20 kHz, and uses silicon carbide transistors. In summary, a prototype dual active bridge was built and tested within 1 year using real-time systems from Speedgoat. It is compact and it can handle powers of 100 kilowatts at 1 kilovolt voltage and has an efficiency of 98%. For testing and tuning the controller, a Speedgoat Performance target machine was used as a flexible, powerful control unit. The controller was deployed to Speedgoat multi-core CPUs and Simulink programmable FPGAs. By using rapid control prototyping, they were able to commission their expensive prototype without any issues. Here we can see a typical architecture for controlling a power converter, where the FPGAs are used for the faster parts of the control involving the analog interfaces and the PWM switching, and the outer loops are used for supervisory and voltage source control. As an example, let us consider the power converter to connect solar panels to the power grid. We start by creating a model of the electrical system in Simulink and Simscape Electrical. The same model used for control design in desktop simulation will later be used for real-time testing. The model we are using includes a solar array with more than 600 panels. This array is connected to a two-level, three-phase inverter via DC link, and this inverter is connected to the grid via relay. Once we design our controller for the solar inverter, we'll use rapid control prototyping to test it with the actual hardware. It is easy to implement the controllers with the different levels of fidelity for the controller at a Speedgoat target machine. Like for example, from MPPT controls, it will go at millisecond range, and the PWM switching will have a resolution of nanoseconds. Once we have a controller ready, we can deploy it to the final control hardware like a microcontroller, and we can do hardware-in-the-loop testing. In this case, the same plant model from Simscape Electrical can be deployed to the target machine. In this way, we test our controller against a virtual plant using the same interfaces it would have with the actual power converter. Here we have a typical setup using a microcontroller as an embedded control. We can test it against a virtual grid-tied inverter running in a Speedgoat multi-core CPU or running on FPGAs, depending on the required level of fidelity. If you're interested in switching effects, you can run in the FPGA with switching frequencies up to 200 kHz. We had initially designed the controller in desktop simulation, As a controller was implemented in the microcontroller, for real-time testing we replaced the controller with Speedgoat driver blocks to interface to the electrical signals. On the left in green we have the analog and SPI outputs. On the right in red we have the PWM capture. The green corresponds to the controller sample time and the red blocks run at the same sample time as the electrical model at 30 kHz. We then deployed it to the target with automatic code generation. The hardware in the loop setup that we will be using includes the microcontroller that contains the final controller. We use a picoscope to see the signals of the interface like PWM and analog signals, and we have a performance real-time target machine to carry out the plant simulation. We start the simulation. First, the controller synchronizes the model to the grid, and after 10 seconds, we connect. So we start generating solar power to the grid with the maximum power point tracking. We can see in the orange current that the irradiance changes. As the irradiance changes, the current will also change. This, for example, would correspond to a cloud passing over the solar panels. That would reduce the irradiance and thus reduce the current. We can also zoom in to see the PWM switching. And also we can go with the scope and see different signals within the model. For example, here we can see the switching dynamics at 5 kHz. Now let's discuss real-time applications for power systems, including transmission and distribution, microgrids, and onboard power systems. The challenges for power systems include the modeling of large power grids, for example, of distribution lines with short transmission lines that may be difficult to decouple. Also, it's important to have models with different levels of fidelity and being able to interface them. Real-time testing can support this with manual and automatic partitioning, concurrent execution in multiple cores and multiple target computers, as well as partitioning by level of fidelity. Other challenges include the interface of the real-time simulation to other components, like communication protocols or even power amplifiers. Real-time solutions provide off-the-shelf I/O interfaces, communication protocols, as well as the MP3 and IEC 61850. There is a wide range of power amplifiers that can interface to a Speedgoat target computer. Depending on the application, you can perform phasor simulation or electromagnetic transient simulation. As an example, let us consider an IEEE European test feeder having 906 three-phase buses, that is 2,718 nodes, and 55 loads. This network will be simulated using a phasor approach. We can segment to allow concurrent execution in multi-core CPUs. Segmenting the model allows for larger models to be built more efficiently. You can also save time by constructing the model automatically. The model segmentation also facilitates data replay through subsegments and provides a more efficient route to simulate real time. Segmenting the model introduces algebraic loops, which must be broken. This means there will be small transients introduced into the segmented system response compared to the full model. We can, however, mitigate this effect. We can also define how concurrent execution will be setting up the different tasks on the real-time target machine. We can also generate code from Simulink and Simscape Electrical and build a model to run in the real-time target machine. Because of the size of the network, this requires several minutes using distributed computing for generating code from different reference models. At the end, a single model is generated which can be used to deploy to the target. Now we can deploy the real-time application, in this case from the MATLAB command line. Once the application starts, we can open SEI to find the simulation results that are being streamed. We can observe the results of the phasor simulation and inspect different voltages and currents. You can use MATLAB scripts to automatically build the network. IEEE network data are parsed by MATLAB scripts that generate the Simulink model. Here you can see a visual demonstration of how such a network can be built. Of course, this can be automated without any visual representation. And this is how this IEEE 123 node feeder would look once built. This would be, in this case, an EMT simulation. Another way to interface power system simulations is PowerHill. Our PowerHill solutions offer you some great value adds for real-time simulation. Run your systems at different levels of fidelity depending on what matters. Bigger time steps to oversee the system level or higher resolution to optimize details of the system component controls. I/O modules and connectors are available to tackle shortest round-trip times while keeping ultra-low latency. A typical setup for PowerHill could look like that. It is comprised of a power amplifier in between, a device under test like the three-phase power part of the solar plant, and the Hill simulator. The power amplifier and the Speedgoat real-time target machine are connected through a high-bandwidth fiber optic connection. Speedgoat and MathWorks offer you complete solutions for full electric and hybrid vehicle simulation. For instance, using powertrain and vehicle dynamics block sets, you can rapidly assess electrical powertrain capabilities. These tools provide you with a great starting point to build great vehicle models with open and well-documented reference applications, ranging from multi-model hybrid electric to pure electric vehicle architectures. The inbuilt libraries provide you a quick access to a manifold of components, including electric drives, battery models, electrical machines, and electrical motor controls. These are Simulink-based, very fast-running models that you can fully customize and instrument and that are ready for Hill deployment and closed-loop simulation with your controls. The same model can be used to support you with different tasks like developing and testing energy management supervisory controls, integrating more detailed battery management systems, or even design torque vectoring control capabilities. Let's for instance consider torque vectoring for a full electrical vehicle with two-motor traction system. At any point in time, the BMS supervisory control needs to determine the torque or power split between the two available electric motors, which are subject to constraints. Constraints include actuator torque and battery current, as well as state of charge. The energy management controller should also attempt to minimize energy consumption and maintain drivability of the vehicle. To efficiently design and test torque vectoring controls, you'll need a detailed model from the electrical, powertrain, and vehicle dynamics block sets. For instance, in this demo, we demonstrate the impact that torque vectoring has the maneuvering on turning radius, ultimately improving vehicle ride handling. For high-fidelity hybrid and electric vehicle modeling, you can also use Simscape and Simscape vehicle templates. Simscape vehicle templates enable you to easily explore powertrain model architectures for conventional, hybrid, battery electric, and fuel cell vehicles. The tool enables you to create high-fidelity and multi-domain physical custom vehicle models tailored to your electrification tasks. For instance, you can easily switch between single to dual or even multi-wheel drive architectures, and at any time increase fidelity and complexity of the model. Perhaps you're working on battery systems design and you would like to analyze battery thermal behavior with an active cooling system. All system vehicle template configurations are compatible with real-time execution using Speedgoat hardware and Simulink real-time. Adding hardware connectivity and preparing the model for real-time simulation only takes a few clicks. With the help of Simulink real-time, you can perform real-time runs of full vehicle models in seconds and start evaluating and comparing new system designs, size components, measure the impact of your decisions with detailed real-time analysis. As well, test early prototypes or embedded controllers with high-fidelity vehicle digital twins. For more complex vehicle simulators, you can rely on distributed solutions integrating multiple Speedgoat target computers interconnected via shared memory or PTP IEEE 1588, and benefit from the know-how and experience of Speedgoat for standardized and highly modular rack solutions. In the same way as electric vehicles, electric ships and more electric aircrafts also have onboard power systems. In this demo, We present the hardware-in-the-loop testing of the microgrid architecture of a fully electric chip. We will be implementing an industry reference architecture from the Electric Chip Research and Development Consortium. The two-zone on-board grid will be deployed to a Speedgoat target computer with 4 cores at 20 kHz. Such model covers not only electrical components, but also gas diesel engines, power electronics, batteries, and electric motors. Actually, the microcontroller under test will be controlling a propulsion motor using field-oriented control. The propulsion motor is modeled as a permanent magnet synchronous machine with an average converter. The field-oriented controller was first designed in desktop simulation and then deployed to a Texas Instruments C2000 microcontroller. Once the desktop simulation behaved according to the expectations, the Simulink model was modified to include the communication with the Speedgoat target computer. In this case, interface for analog, quadrature, and PWM. In this way, the interfaces to the embedded controller are the actual encoder, PWM, and analog signals. We can think of a related success story from Leonardo DRS. While in our previous demo we used CPU simulation, Leonardo DRS used Speedgoat FPGAs to perform microcontroller scale hill testing of their shipboard power electronic system. By using hardware-in-the-loop testing, Leonardo DRS reduced design iterations, reduced cost, and saved time as well as lab space. As a final topic, let's discuss the real-time applications for power and energy management. Real-time testing is also a powerful tool supporting development of power management solutions, like battery cells, fuel cells, and pumped storage. Typical challenges include the development of battery management systems and fuel cell controls. Also, developing reliable state estimation algorithms for state of charge or state of health of batteries is not trivial, and you also need to interface with other system components with communication protocols like CAN or EtherCAT. Rapid control prototyping can be used to address such challenges and also provide an off-the-shelf I/O connectivity and communication protocols. Other typical challenges include testing of controls and interfaces like battery cells or chargers. Thorough testing of control firmware under realistic conditions is not trivial. Using hardware-in-the-loop testing, you can validate your power management algorithms. Let's have a look at an example for BMS. Good reasons to carry out hill testing of BMS are that you can model battery cells with Simulink and Synscape Electrical. There are many available models to get started. That you can perform accelerated testing for charge and discharge cycles that would typically take hours. And also that you can reproduce design issues and fault conditions that may be difficult and involve safety considerations. And also that you may want to test for each software revision or design iteration that becomes available. And finally, when you use cell emulators, you can increase the confidence in your design iteration, as you can also test the analog frontends and validate your algorithms for cell balancing, state estimation, among others. Here we have a battery model with 16 cell modules, each with 6 cells connected in series. Each battery cell block includes electrical and thermal behavior. The charge and discharge of the battery pack is also modeled, and the individual cell voltages as well as their temperatures are measured and sent to the BMS controller. When we execute the battery pack model in real time, we can observe signals of our interest, like the voltage and current of the battery pack, as well as tune parameters. Once the real-time execution is over, we can also verify that the model execution time was well below 1 millisecond with no CPU overloads. We start with a test model which allows us to simulate battery cells and generate fault scenarios. To simulate a fault, we added a switch that allows us to short 2 cells without physical consequences. A control current source block is used to simulate the charge or discharge current with the help of a slider block. To perform diagnostics on cell level, we measure the voltage between 2 cell terminals. The measured cell voltage values are fed into a block that represents the battery cell emulator from Speedgoat, which converts these numerical values into electrically isolated voltages in real time, each relating to the individual battery cell being simulated. The BMS controller performs diagnostics on cell voltages and generates a fault status for overvoltage or undervoltage faults, as well as short circuits between 2 terminals. In this case, the BMS controller outputs its status on a digital output port. Upon executing this model in real time, we can change the current level for any overvoltage or undervoltage fault from the controller. We don't see any fault yet, but when we inject a short circuit fault, we can immediately notice the warning light. Let's look at the results in the simulation data inspector for the whole experiment. We can notice small changes in cell voltages due to change in current, and one of the cell voltages dropped significantly as we trigger the fault, and we can see the corresponding change in the fault status. The battery cell emulator from Speedgoat is designed to accelerate BMS testing. You can source or sync up to 5 amperes for each cell, with a maximum output voltage of 6 volts. And you can have up to 190 cells in series. Therefore, when emulating lithium-ion technology, you can emulate a battery pack of around 800 volts DC at full charge. You can also include fault insertion and temperature simulation at cell level. And you can use Simulink and Simscape Electrical to model the battery cells and deploy to a Speedgoat real-time system. Each emulated battery cell will have the electrical behavior given by your model dynamics. And for each battery cell, you can also have optional modules to emulate temperature sensors for each cell and to test fault conditions like broken wire and short circuit. Let us conclude with 2 success stories on power management. First, let us talk about how Leclanché Energy Storage Solutions is developing the next generation of lithium-ion battery packs for autonomous vehicles. Being unable to properly test and verify new BMS algorithms before operation with real battery packs, Leclanché started using Speedgoat battery cell emulators for hardware-in-the-loop testing of their BMS algorithms. As it is typically required, such tests required also fault insertion and some communication protocols, in this case CAN bus. They were able to thoroughly validate their BMS and state estimation algorithms using Speedgoat real-time solutions, thus reducing test time by around 50%, increasing coverage, and finding bugs at an early stage. The second success story is from Nuvera, a company developing fuel cell technology for commercial vehicles. Their technology uses both fuel cells and lithium-ion batteries, and they use Simulink and Speedgoat hardware for quick iterations in their designs without having to put a real engine at risk. When installed in forklifts, their fuel cell engines would reduce 128 metric tons of CO2 annually each. We have covered many topics during this webinar on electrification, from system to component level. To conclude, I would like to emphasize our 3 key takeaways. First, you can use Simulink and Speedgoat hardware as a unified platform for developing power electronic converters, electric motors, energy management, and power system controls. Second, that real-time testing is a key step between desktop simulation and embedded code generation for developing electrical systems. And third, that you can use hardware-in-the-loop simulation together with test automation to thoroughly test embedded controllers, electrical components, battery management systems, or even power system controllers.
You want to learn more about real-time controls testing? Then find additional content linked here.